Dear students, today we'll see the second part of DCET question paper for 2021. So let's start with the questions. Question number 21. The above diagram shows ideal graph for which filter? Option A is high pass filter, option B is low pass filter, option C is band pass filter, and option D is band rejection filter. So if you see the diagram, now in this diagram, it is gain versus frequency. So here you have gain and x-axis is frequency. And in that we have shown a pass band. So this is a pass band. Say if it starts from 0, we'll have F1 here. And then there is a stop band. The gain is less here. And then again there is a pass band. Then again there is a pass band. So let this cutoff frequency be F2. So between frequency F2 and F1, that is F1 and F2, the band is stop band. It is the attenuation range. It is the range where the signals of those frequencies between F1 and F2 are rejected. So it is a band which is rejected. So here you are having a frequency band which is rejected. So this is band rejection filter. So from this option 4, that is option D, that is band rejection filter, is the right answer. We are going to reject a band of frequency from F1 to F2, and rest other all frequencies that is below F1 and above F2 will be passed. So here we can see the above diagram shows ideal graph for band rejection filter. Then we'll go to the next question. Ionospheric propagation is also called as what? Ground wave propagation, space wave propagation, sky wave propagation, or line of sight propagation. Now in a radio or communication, we know that sky wave refers to the propagation of radio waves reflected back towards Earth from the ionosphere, which is an electrically charged layer of the upper atmosphere. It is mostly used in shortwave frequency bands. Therefore, ionospheric propagation is also called as sky wave propagation. So here option C will be the right answer. Ionospheric propagation is also called as sky wave propagation. So here we can see option C is the right answer. Then we'll go to the next question. In T-type attenuator, the series arm R1 is given by. Now if you see the figure of T-type attenuator, we can draw the figure like this. We can have this as R1, then this as R2, this as R1. Okay, so this is R1, R1, R2, and this circuit will be having its design impedance, design resistance as R0. Okay, and this is your input here. So this is an T-type attenuator. Now in this T-type attenuator, when we studied with R0 as our characteristic impedance, we know the formula for the series arm R1. R1 is the series arm and R2 is the parallel arm or shunt arm. So for series arm for T-type attenuator, the formula was R1 is equal to R0 into N minus 1 upon N plus 1. And similarly, the R2, that is the parallel arm, that is the shunt arm, was given as 2N upon N square minus 1. So these were the formulas of series arm and the shunt arm for a T-type attenuator. Similarly, you can also get the series arm and shunt arm, that is R1 and R2 expression for pi-type attenuator also. But in this question, it has been asked for T-type attenuator. So for T-type attenuator, the series arm R1 is given by. So this is the series arm. R1 is given by this expression, that is R0 into N minus 1 upon N plus 1. So here in these options, we can see option A is the right answer. R1 is equal to R0 into N minus 1 upon N plus 1. So here you can see R0 is equal to N minus 1 upon N plus 1. Okay. Then we'll go to the next question. Series impedance in transmission line is given by. So whenever we have a transmission line, so this is a transmission line, we can have a series impedance, and we can have parallel admittance, that is shunt admittance. So we can have shunt admittance. Now the series impedance, that is Z, it is denoted by Z, is given as R plus J omega L. This is series impedance per unit length per phase. Similarly, the shunt admittance, we can take Y as G plus J omega C. So this is shunt admittance per unit length per phase. Now in this question it is asked as series impedance in transmission line is given by. So series impedance is Z, which is given by R plus J omega L. So here you can see a resistance plus J omega L is the series impedance in transmission line. So option B is the right answer here. So here you can see option B is the right answer. Then we'll go to the next question. If Vm is equal to 5 volt and Vc is equal to 6 volt, then modulation index in amplitude modulated wave, that is AM wave, is given by what? Now we know that a theoretical formula for modulation index in amplitude modulated wave, M, is equal to Vm by Vc. Now in this question, the value of Vm and Vc are given. So Vm is 5 volt and Vc is 6 volt. So it is 5 upon 6. So 5 upon 6 is nothing but 0.833. Okay. Now modulation index is always given in percentage. So M in percentage is nothing but 0.833 multiplied by 100, which is nothing but 83.33%. So option D will be the right answer here. 83.33% is the modulation index in AM wave if your Vm, that is voltage for modulating signal, is 5 volt and the voltage for a carrier signal is 6 volt. So if that is taken, if that ratio is taken, we'll get the modulation index, that is Vm by Vc. So here you can see 83.33 is the right answer. Then we'll go to the next question. Line encoding or converts digital data to analog data to digital data to sequence of voltage levels, analog data to sequence of voltage levels. Now we have studied line coding methods. Okay. Now line coding was nothing but it was a process of converting digital data into digital signal. So it is going to convert digital data into digital signals. Say for example, we have digital data as 1, 0, 1, 0. We can use a way to represent that. We can have a pulse for 1, no pulse for 0. We can have pulse for 1, no pulse for 0. So this will be one type of line encoding method. Okay. Now in this, what we are doing, the digital data is going to get a digital signal. The digital data is going to be given in a digital signal. Now digital signal means what? It is a sequence of voltage levels. It is a sequence of voltage levels. So line coding converts a sequence of binary bits to digital signal, digital data to sequence of digital levels. Okay. So option C will be the right answer here. Digital data to sequence of voltage levels. So here option C is the right answer. Then we'll go to the next question. This modulation technique produces only 1 bit per sample. Now we have studied pulse code modulation, PCM, then a delta modulation, adaptive delta modulation, and differential pulse code modulation. Now in PCM, that is pulse code modulation, we use the process of sampling and quantization and we converted analog signal to digital signal. Whereas in delta modulation, we used a staircase waveform, which was hunting the message signal. So if this was your information signal, then we had a staircase waveform which was always hunting the information signal. And here, every time, every time period here is the sample. It's bit per sample. And here, depending upon the staircase is above the analog wave or below the analog wave, we are going to decide that every sample we will be taking as one bit, either 1 or 0 or 1 it is, or depending upon whether the staircase waveform is above the information signal or below the information signal. So this modulation technique is nothing but delta modulation technique. So the modulation technique which produces only one bit per sample is delta modulation. So option B is the right answer here, delta modulation. Then we'll go to the next question. According to Shannon's theorem, relation between rate of information and channel capacity. Rate of information is given as R. Rate of information is given as R and a channel capacity is given as C. Okay, so if information rate R is less than a channel capacity C, then the transmission of data may be done without error in the presence of noise. And on the contrary, if the information rate R is greater than the channel capacity, then errors cannot be avoided regardless the coding techniques used. Okay, that means for a proper transmission without error, the condition given by Shannon theorem is the information rate R should be less than the channel capacity C. So here option A is the right answer. That is information, that is rate of information R is less than channel capacity C. So here you can see option A is the right answer. Then we'll go to the next question. The statement not correct about optical fiber cables. So if you just see the statements and then we'll find out which statement is not correct. So the first statement is the optical fiber cable have higher information carrying capability. This is correct. It has higher information carrying capability as compared to the conventional cables. Option B is have more signal attenuation over long distance. This is wrong. It does not have more signal attenuation for long distance. Option C is these are much lighter than copper cables. This is correct. Option D is these are expensive and more difficult to install than other cables. This is correct. That means option B is the statement which is not correct for optical fibers. So have more signal attenuation over long distance is the not correct statement for optical fiber. So here you can see option B is the answer for this. The statement which is not correct for optical fiber cables is it has more signal attenuation over long distance. Then we'll go to the next question. Which of the following is disadvantage of a digital communication system? So if you see the options, a transmission of digital signal requires circuits with a very large bandwidth. Option B is noise and interference are less. Option C is digital signal or characteristics are convenient for electronic switching. Option D is digital circuits are more reliable in digital communication. So out of these options, the first option, that is option A, transmission of digital signals requires circuits with very large bandwidth is a disadvantage. So it requires a large bandwidth as compared to analog communication system. So here option A is the right answer, that it is a disadvantage. So here you can see the disadvantage of digital communication system is that a transmission of digital signal requires circuits with a very large bandwidth. Then we'll go to the next question. In this type of modulation, the bit rate is higher. Now the options are phase shift keying. It is the basic phase shift keying. Second is a differential phase shift keying, that is DPSK. Third is a quadrature phase shift keying, that is QPSK. And fourth is amplitude shift keying. So out of this, the phase shift keyings in that only will get the higher bit rate in a quadrature phase shift key, that is QPSK. So here you can see a binary phase shift keying is a straightforward modulation scheme that can transfer 1 bit per symbol. A quadrature phase shift keying is more complex but doubles the data rate, or it achieves the same data rate with half bandwidth. That means the data rate for a QPSK, that is a quadrature phase shift, is high. So here you can see in this type of modulation, the bit rate is higher, that is a QPSK, which is nothing but option C, a quadrature phase shift key. Then we'll go to the next question. The sequence of operation carried in pulse code modulation, that is for PCM. So from these options, we can see that option A is sampling encoding a quantization. Option B is sampling a quantization encoding. Option C is a quantization encoding sampling. And option D is a quantization sampling encoding. So we know that when we studied PCM, so we had a analog wave, and then the first analog wave was quantized. It was quantized with different levels for sampling time period. Okay, and those quantized values were then encoded so that they were put in binary format. So it is sampling, then we have quantization, and then encoding. Okay, so sampling, quantization, encoding is the option B here. So option B is the right answer. That is a sequence of operation carried in pulse code modulation. So here you can see option B, that is sampling, quantization, encoding, is the right answer. Then we'll go to the next question, question number 33. Energy coupling method used in waveguide is, options are a transformer coupling, direct coupling, probe coupling, or RC coupling, that is resistor capacitance coupling. So from this type of couplings, the energy coupling method used in waveguide is probe coupling. So option C is the right answer here. Probe coupling is used for coupling the energy in waveguide. Then we'll go to the next question. The dominant mode in rectangular waveguide is, so the first one is T, that is a transverse electrical 1-1, or transverse electrical 1-0, transverse magnetic 0-1, and transverse electrical 0-1. So in this, the option B is the dominant mode, which is a transverse electrical 1-0. So here you can see the dominant mode is TE10. Then we'll go to the next question, question number 35. Electromagnetic waves are transmitted through. Okay, so electromagnetic waves are one which can be transmitted either in open air, that is the free space, or through waveguide. So here out of these four options, coaxial cable, or twisted pair, optical fiber, and waveguide will be the right answer. So here you can see option D is the right answer. Electromagnetic waves are transmitted through waveguide. Then we'll go to the next question, question number 36. Display techniques used in radar is, whether the display is done by the method of amplitude modulation, frequency modulation, deflection modulation, or phase modulation. Obviously, it is option C, deflection modulation. Deflection modulation is a method used to display the output in radar. So here we can see the concept, display methods in radar system. The output of a radar receiver may be displayed in any of a number of ways. The following three being the most common are display methods in a radar system. That is, number one, deflection modulation of a cathode ray tube, that is a CRT tube screen, as in A-scope method. Then intensity modulation of a CRT as in plan position indicator, that is PPI, or direct feeding to a computer. So here is the answer is deflection modulation for this question. So here you can see a display technique used in radar is option C, deflection modulation. Then we'll go to the next question. The typical uplink frequency in satellite communication is how much? 1 gigahertz, 2 gigahertz, 4 gigahertz, or 6 gigahertz. Now we always know that the uplink frequency will be higher than the downlink frequency. So for a standard satellite communication, the uplink frequency is 6 gigahertz and downlink frequency is 4 gigahertz. So here you can see this is the uplink frequency. So here we have the transmitter. So this is the transmitter, and it is going to give the uplink frequency, and uplink frequency is 6 gigahertz. Then it will go to the satellite and reflect back. So this is a satellite, and when it is reflecting back, it is downlink frequency. Downlink frequency is taken as 4 gigahertz. So uplink frequency is 6 gigahertz. So it comes in C band, and this is the standard uplink, standard satellite frequency for uplink. So here you can see the typical uplink frequency in satellite communication is 6 gigahertz. Then we'll go to the next question. Subscribers' permanent data is stored in. Okay, so this is on mobile communication. So options are visitor location register VLR, home location register HLR, equipment identity register EIR, interworking location register ILR. So here subscribers' permanent data, all the basic data of the subscriber is stored in home location register, that is HLR. So here you can see the HLR definition. The home location register HLR is a database used for storage and management of subscriptions. The HLR is considered the most important database as it stores permanent data about subscribers, including a subscriber service, profile, location information, and activity status. When an individual buys a subscription in the form of SIM card, okay, then all the information about this subscription is registered in the home location register HLR of that operator. So here you can see option B is the right answer, that is home location register. Then we'll go to the next question. The standard belonging to second generation cellular network is. Options are Nordic Mobile Telephone NMT, Advanced Mobile Phone System AMPS, Global System for Mobile Communication GSM, and option D is European Total Access Communication System ETACS. So when we speak about second generation cellular network, it is Global System for Mobile Communication. So GSM was the second generation of cellular network. So option C is the right answer here. So here the Global System for Mobile Communication, that is GSM, is a standard developed by the European Telecommunication Standards Institute ETSI to describe the protocols for second generation, that is 2G digital cellular networks used by mobile devices such as mobile phones and tablets. So here option C will be the right answer, that is Global System for Mobile Communication GSM. Then we'll go to the next question. Message switching is also called as dash technique. So out of these 4 options, the first option is get and hold, second option is store and release, third option is store and forward, and fourth option is store and never release. So out of this, the option C, that is store and forward, we have to store the message at a particular node, and depending upon the path which is there to go to the next node, we have to forward it. So it is store and forward. So message switching is also called as store and forward. If you see the concept of message switching is a switching technique in which a message is transferred as a complete unit and routed through intermediate nodes at which it is stored and forwarded. In message switching technique, there is no establishment of a dedicated path between the sender and receiver. The destination address is appended to the message. Switching provides a dynamic routing as the message is routed through the intermediate nodes based on the information available in the message. Message switches are programmed in such a way so that they can provide the most efficient routes. Each and every node store the entire message and then forward it to the next node. This type of network is known as store and forward network. So here option C, that is message switching, is also called as store and forward network or store and forward technique. Okay, so this is the answer, that is option C is the answer for this question. Thank you, students.